Yes, so good afternoon, everybody. I will continue today on our workshop about quantitative methods in sociology. And so last class, we talked about sample weights. And today, and I gave some examples focusing more on descriptive statistics, more on frequency tables and also cross tabulations. And today I will go into the linear regression, the ordinary least squares regression. So I will share my screen here now. And if you have any questions throughout the presentation, you can interrupt me or ask questions in the chat. And I probably won't see the question in the chat, so Peggy can read it to me if that's the case. So let's try to open here. So we will continue on the lecture about ordinary least squares regression, the next topic of our workshop. I mean, always when I organize and I go back to my previous lectures about these topics, I always start adding slides and adding slides, but I think we can cover everything today. So this lecture on ordinary least squares regression, I organize it like this way here, giving an introduction, and then explaining what is the multiple correlation, the R square, which is usually reported and widely interpreted in linear regressions. Then I'm going to talk exactly what's the meaning of linear regression, how to interpret coefficients from those regressions. And I'm going to start with a simple example of income as a function of age and education. So age and education as independent variables to explain income. And then I'm going to say that one of the assumptions of the linear regression is that our variables, if they are at the continuous level of measurement, they have to have a normal distribution. So we can just do some quick analysis to see if our variables are normal distributed. And we will see that income is not normally distributed. It's really skewed to the right, concentrated on the left. So instead of using income, I give an example of using the natural logarithm of income as the dependent variable. Then I show some examples of predicted values, how to use specific regression to predict values for the dependent variable, and also show you how to do residual analysis with graphs, and how to include dummy variables as independent variables in your analysis. And all the examples that I give here today are based on the 2018 American Community Survey and only for the state of Texas, right? It's just because it was faster, easier to run. And this data is available in the course website, in the course link there. I provided, and also by the end of this lecture, there is the link of where you can access the do file and all the files related to this lecture. So ordinary least square regressions, they're also called linear regression. Whenever you hear the term, oh, someone estimated linear regression for a continuous dependent variable, so they're pretty much estimating OLS regression. And this is an important technique to estimate associations of several independent variables with a dependent variable. And all these variables, they're supposed to be in the interval ratio level of measurement. What does it mean? That those variables should be continuous. They should not be categorical. But we're going to see that we also can include independent variables in our models as categorical variables, and I'm going to talk later here. Variables are at the interval ratio level, but we can include ordinal and nominal variables as dummy variables. So if I have, for example, years of education, but for me makes more sense to group people by specific subgroups within years of education, those people with less than high school, college, and graduate degree, we can separate, we can group these people into these subgroups and then enter this information about education in our models as dummy variables. And the name linear regression comes from the fact that each independent variable has a linear relationship with the dependent variable. The relationship between the two variables is linear. So the coefficient that we are estimating is linear. Independent variables are uncorrelated with each other. So we have to include independent variables in the model that don't have really high correlation among themselves. But some of these assumptions and also other assumptions, other requirements that we are going to talk later here today, they are often violated. And if they are violated, then this technique will produce biased or inefficient estimates. So we have to be careful to at least be as close as possible to follow the assumptions, the requirements, so we don't have biased estimations in our analysis, okay? So this is examples of a bivariate regression equation. The bivariate regression equation is when we have only one independent variable explaining the dependent variable. And bivariate regression equations are also called simple regressions. And the multivariate regression equations or multiple regressions, we have more than one independent variable. In this example here, we have two independent variables explaining one dependent variable. Sometimes people just use the term simple in an incorrect way. They actually have a multiple regression and they say, oh, I'm going to show you here a simple regression. But simple regression means that you have just one independent variable. So if you have a multiple regression equation, but it's not the final one, and it's not so sophisticated, you should explain that. You should say, oh, I have a multiple regression, but these are preliminary results. I still can make some improvements in the future, but it's, technically speaking, it's not a simple regression. And how is the notation here? The notation, if you will go back to your notes from high school, you will remember it, right? It's pretty much the dependent variable being explained by a constant. In high school, we usually use this notation A plus the slope B, and the slope B multiplies the independent variable. So we get a value for that independent variable for someone, multiply by the slope, add to the constant, then we get the predicted dependent variable for that specific individual, right? The notation that we're going to use here more is going to be with the betas. So beta 0 is the intercept, is our A, and beta 1 is the slope, right? So the intercept is going to be the value of y when x equals 0. X equals 0 times b, 0, x equals 0 times beta 1, 0, so y equals beta 0. So that's where our curve will touch the vertical axis, the y-axis. And the slope is pretty much saying how strong or how weak is y increasing or decreasing, if this signal here is negative, depending on one unit change of x, right? And the multivariate regression equation, it's pretty much similar notation, but now we can add more variables. This example here has only two variables. And the slopes, we call them partial slopes. So for example, beta 1 is the partial slope of the linear relationship between the first independent variable, x1, and y. The partial slope of the linear, beta 2 is the partial slope of the linear relationship between the second independent variable, x2, and y, okay? And when we are talking about this multiple regression, so this is the same notation as we have before. The beta 0 is the y-intercept, is where the regression line crosses the y-axis, exactly when in this example here, when x1 and x2 equals 0, all this portion of the equation will equal to 0, and y will equal to beta 0. Beta 1 is the partial slope for x1 on y, and beta 1 indicates the change in y for 1 unit change in x1, controlling for x2. So if we change x1 by 1 unit, it will change y by beta 1 units, controlling for x2. And beta 2 indicates the change in y for 1 unit change in x2, controlling for x1. Okay? So this term here, controlling. The partial slopes indicate that the effect of each independent variable on y, while controlling for the effect of the other independent variables. This control here is called, like in regression analysis, ceteris paribus, this Latin term, which means other things equal, other things held constant, all other things being equal. So what does it mean exactly to analyze the effect of x1 on y, maintaining constant x2, and vice versa, the effect of x2 on y, maintaining constant x1? So in this diagram here, I try to explain it. When we say maintaining constant, I'm not saying that I'm collecting information just for people with one specific characteristics on x1 and one specific characteristic on x2. I'm actually collecting information about everybody. And for example, this example here, already my y, my dependent variable is income. My x1, my first independent variable is, in this example here, education. And my x2, my second independent variable, is experience in the labor market. How many years I have of experience working in the labor market. Some databases don't have this variable. Most databases don't have. For example, the American Community Survey doesn't. And instead of using experience, we use age as an approximation, as a proxy to experience. But let's just, in this diagram, make something really simple here now. Let's say that someone can be categorized only by having low or high education. So all these dots here are people that I interviewed with my questionnaire. And I asked them 3 questions. What's your income? Do you have high or low education for whatever threshold I'm analyzing, low or high? Let's just think about low or high. And I ask if they have low or high experience in the labor market, right? So each one of these dots, it's gonna be one individual that I collected questionnaire. Some of them will have low education and high experience in the labor market. Some of them will have low education and low experience in the labor market. Some of them will have high education and high experience, and then high education and low experience. So when we are trying to understand the effect of education on income, when I say that I want to analyze the effect of education on income, I have to compare people that have low education with people that have high education, maintaining experience constant. So I have to compare these people here with these people here. And I compare these people here with these ones. So I vary education, but I maintain in this example experience high, and in this example experience low. So this is how I estimate the beta 1. The beta 1, how is it? It's pretty much, I have to compare this subgroup here with this subgroup here. So education is varying from low to high, and experience is constant. And I compare these 2 other subgroups here, in which education also varies from low to high, and experience is constant on low experience. And this aggregated effect here is summarized by beta 1. And I'm going to show you the formula for beta 1, which we actually don't have to know it to do the calculation by hand because Stata will calculate beta 1 for us. But this logic here is important to understand, right? You are comparing people with different educations, similar experience, to analyze beta 1, to estimate beta 1. And you do the same thing for education, for experience. If I want to see the effect of experience, beta 2, on income, I have to compare this subgroup here that has high experience with this one here that has low. So experience is varying from high to low, but education is constant, low education. And I compare this group here with this group here. High experience, low experience, maintaining high education constant on high. So experience varies and education is constant. The aggregation of these two effects here will result on our beta 2, okay? So beta 1 is if I change education from low to high, how much my income will increase, and experience, if I change it from low to high, how much my income will increase, controlling for education. And here was controlling for experience. And the U term here can also be symbolized by E. The error term is variation on income that's not explained by any of my independent variables, okay? So that's how the logic of the estimation is done. We estimate beta 1 and beta 2, in each one of them controlling for the other independent variable. So the interpretation of partial slopes, the partial slope shows the effects of the independent variables in their original units. These values can be used to predict the scores on Y. Partial slopes must be computed before computing the y-intercept. So now I'm going to show you the formulas to estimate beta 1, beta 2, and after we estimate beta 1 and beta 2, we can estimate beta 0. But remember, you don't have to calculate it by hand. You just have to understand this logic here, right? But how exactly beta 1 and beta 2 are estimated? We pretty much get the standard for beta 1. We get the standard deviation of my dependent variable and divide by the standard deviation of the first independent variable, which is x1, and multiply it by the bivariate correlation between y and x1, which is the ry1, subtract by the bivariate correlation between y and x2, multiplied by the bivariate correlation between x1 and x2. So I'm trying to see how y and x1 are correlated with each other, already discounting correlations of y with the other independent variable, which is x2, and also discounting by the correlation between the two independent variables with each other, x1 and x2. And that is divided by 1 minus the correlation, again, between the two independent variables. And the beta 2, I will just, instead of using information about x1, I will use about x2, instead of x1 and x2, and here I invert, okay? So the formula here, it can all be estimated based on these bivariate correlations. Remember what is bivariate or bivariate regression? Is the simple regression. What's the direct correlation of y and x1, but Here I'm discounting for possible correlations that y has with the other independent variable and of the two independent variables by themselves. Look at this example. Just going back here in the formula. I have only two independent variables, right? I have only two independent variables, and these are how the coefficients are estimated. If I had more independent variables in my analysis, this formula would be much longer, right? I'm just showing here the logic to estimate beta 1 and beta 2. After I estimate beta 1 and beta 2, as I said in the previous slide, I can estimate the constant, beta 2. So now I calculated beta 1 using this formula. I estimated beta 2 using this formula. And now I can pretty much just get the mean value of x2, the mean value of x1, and the mean value of y to estimate the constant. It's pretty much I just get the mean of each one of the three variables, multiply by the constant, I get beta 0. Okay? Do we have to calculate, remember these formulas? No, we have to understand the logic, and it's more important to understand the interpretation. So here, one example. And in this example, as I said, I don't have experience in the labor market in ACS, in the American Community Service, so I use age. And in this example here, I'm use age as a continuous variable. So it goes from 18 until 18 plus, people with at least 18 years of age. And education groups, I have 5 education groups, less than high school, I think it's associate degree or junior college, and graduate school. So the beta 0, beta 1, and beta 2 that I just estimated before are these numbers here, right? So this one is my beta 1 that I estimated from here. My beta 2 is this one here, and this is beta 0. So how do I interpret this 724? If I increase age by 1 year, I will increase my income by $724. Education group. Education group is not measured by years of schooling, in this case years, jumping from these groups that I said. So jumping from less than high school to high school, for example, will increase my income by $18,000. Controlling for education. Oh yeah, controlling for age, right? And for age, the same thing. 1 year of age, if I increase 1 year of age, my income will increase by $724, controlling for education group. If I move from someone from less than high school to high school, my income will increase on average $18,000, controlling for age. And this is the important thing. These coefficients are averages, right? That's an average based on the data that we have, on the data set that we have. And this is something weird that we have in this estimation here. The constant, the beta 0, is negative. It's pretty much saying if age is 0 and education group is 0, then the constant is going to be negative. But actually, our data set for this analysis doesn't have age equals 0 because I'm estimating this result here only for people with at least 18 years of age or 15 years of age. Okay? But that's the reason that we usually don't interpret the constant. The constant is taken into account to estimate predicted values of my dependent variable, but I usually don't interpret it because here's more mathematical adjustment of my equation. I have to report it in the tables, but I don't have to interpret, okay? And I will interpret the rest of this regression as we go on this lecture. Oh yeah, there is one mistake here in this regression. Which one is it? Based on our previous lecture. I did not.
There is no weight.
There is no weights. I did not include weights in my analysis, exactly. So I have to include weights. I don't remember. Oh, so it's right here, how we do it. If we want to do it for tables, to expand the population size, we can use F weight if my weight variable is discrete, and I weight if it's a continuous variable. If I want to maintain the sample size, I use A weight. And for statistical regressions, the best way is to use the P weight because estimate robust standard errors. And we also saw that some surveys, such as American Community Survey, has a complex survey design. So we have to inform the complex survey design, and we inform the P weight within that comment. And that's exactly this exercise here. SVY set, I'm informing the complex survey design, the variable cluster that exists in my data, the P weight, variable for the individual weight, PERWT, and the variable strata under the option strata. And I estimate the same regression, but now putting SVY column before, it takes into account the complex survey design. You see that the coefficients, in this case here, they changed. For example, from 724.30 to 796.34. 18,177 to 16,863. So these are the correct coefficients to analyze when I'm using data from the American Community Survey, for example, because I took into account the P weight and I took into account the complex survey design. So the correct coefficients tell us that for each additional year of age, people make on average $796 more, controlling for education groups. If I move from one education group to the next one above it, I increase on average earnings of these individuals by $16,863, controlling for age, right? So that's the interpretation of the coefficients. That's beta 1, that's beta 2, and that's beta 0, right? So here I'm just focusing on the coefficients now. So let's talk more to understand the rest of the regression. We can also estimate what are called the standardized coefficients, and they are symbolized by the B asterisk or B star. The partial slopes, beta 1 and beta 2, the ones that we just estimated in that regression, are in the original units of the independent variables. What are the original units of the independent variables in my example? Age is 1 year of age from 15, 16, 17, 18, and so on. And years and education is in 5 education groups: less than high school, junior college, and graduate degree. Okay, so I have different units. I have different units between age and education. So it's not correct to analyze the magnitude or to compare the magnitude of the coefficients of age and education to see which one is stronger, because the unit of analysis is different between these two independent variables. So this makes assessing the relative effects of independent variables difficult when they have different units. In other words, which independent variable has the stronger effect on my dependent variable? The coefficients, beta 1 and beta 2, do not provide that good information because the two variables are in different units. It is easier to compare the magnitude of the effects of these two independent variables on my dependent variable if we standardized to a common unit converting to z-scores. We pretty much compute these, what are also called beta weights or standardized coefficients. So beta weights, standardized coefficients are the same thing. To compare the relative effects of the independent variables, to compare the magnitude. The magnitude of the two independent variables, the effects of the two independent variables on the dependent variable. And how do we interpret these beta weights? They're going to tell us the amount of change in the standardized scores of y for a 1 unit change in the standardized score of each independent variable, while controlling for the effects of all other independent variables. Another way to interpret it is that they show the amount of change in standard deviations in y for a change of 1 standard deviation in each one of the independent variables. See, this interpretation is not so easy to understand as it was when we had the original units of age and education group, because that was easy to understand. 1 additional year of age generates an impact on income in dollars. If I change from one education group to the other, that will generate an impact on earnings in dollars. Now it's always standard deviations. The interpretation might be weird, but I'm not really interested on analyzing these effects. I'm just comparing the effect of beta of x1 and the effect of x2. How do we calculate it? This is the formula. You pretty much just get the original coefficient for each one of the variables, or the coefficient, the coefficient for x1, the coefficient for x2, and that's the standard deviation of x1 divided by the standard deviation of y. Same thing, standard deviation of x2 divided by the standard deviation of y. And then we estimate the standardized coefficients, which are now normalized. They have an average of 0, and they vary across the 0 to higher or lower values, right? The regression now is symbolized like this. Our constant is symbolized by the AZ. The beta weight, as I said, is the B star or B asterisk. So we have the B1 star, B2 star. And these variables, they have been standardized to the Z-score. If you remember from Introduction to Statistics, the Z-score for each variable, it's pretty much the value, for example, my age minus the average age in the overall sample divided by the standard deviation of age in the overall sample. So I calculate the Z-score for each individual. It's kind of like I'm using this new variable here, Z1, this new variable here for Z2, to estimate beta 1 and beta 1 star and beta 2 star, right? And also income is standardized. I get the individual income of someone minus the average earnings divided by the standard deviation. Can you say what the Z-score was again for a refresher? This is the Z-score, right? Let's say that someone is 30 years old, right? So let's say that, pointer, pen. Let's say that my variable age for person 1, this one here, is 30. I have someone with 30 years of age. I know from that data set that the average age of people in that data set, I'm just trying to make something easy here, it's gonna be 40, right? 40 years of age. And let's say that the standard deviation of age, because like some people have more than 40 years of age and some people have less, so I just calculate the standard deviation of age. So this is my variable age here in this example, right? And the standard deviation that I calculate for age for my variable 1 is, let's say that it is 5, only 5. So what's going to be the z-score for this individual? The z-score for that individual for the variable age, it's going to be 30 minus 40. This is really beautiful handwriting. 40 divided by my standard deviation 5. So 30 minus 10 minus 40 is going to be minus 10 divided by 5. I'm going to have minus 2. This is a 2. This is a 2. Okay? This specific person had an age that it was lower than the average. So the z-score of that person is negative. If someone had an age that was higher, let's say for someone who is 50 years old, 50 minus 40, 10, divided by 5, 2. So that person is going to be above 0. This z-score is going to have pretty much a mean equals to 0, and some people will have positive values if they are above the mean, or negative if they are below the mean. And the other thing, to understand the mean equals to 0, for example, if someone is 40 years old, that the age of that person equals the average of age in the whole database. So it's going to be 40 minus 40, 0. 0 divided by 5, z equals 0. Okay? You could create a variable which would be the z-score of age here, the z-score of education, and the z-score of income, and then estimate the model using these 3 new variables to get the beta stars. But we don't need to do that in Stata, right? We don't need to create zy based on y, or z1 based on x1, or z2 based on x2. Stata already calculate the B star, the standardized coefficients, by simply including this option here after the regression, right? And look here, these are my notes from Stata. I'm estimating the standardized regression coefficients, also called the standardized partial slopes or beta weights. Whenever I include this option here in Stata to calculate the coefficient, the standardized coefficient, it does not allow the use of the complex survey design. That's the reason that I'm using the P weight, right? We use P weight to maintain the sample size. So the sample size is the same, 127. And we are estimating standard, robust standard errors. But if we go back to how the regression was before, this one is the regression that we use, the complex survey design, 796. It's the same thing here, 796. The fact that I use the P weight instead of the complex survey design, as I mentioned, the complex survey design usually corrects the standard error, but the coefficient is the same, right? But in this specific example, even the standard error is similar from this regression here, only with the P weight, and the previous one with the coefficient. Oh no, it's different. With the, yeah, that's good, good example. This one here has a complex survey design, 796, 11.7. Without the complex survey design, 796 is the same thing, but see, the standard error is now different. It was 11.7, right? And now here's 11.4. So, but the P weight at least calculated the coefficient correctly. And that's what matters at this point here, right? I'm not analyzing this portion of the regression at this point. I'm not analyzing this. I'm analyzing only this. And then because I put the option comma beta, Stata deleted that confidence interval that was here and included the betas, the standardized coefficients. And there is no standardized coefficient for the for the constant, the y-intercept will always be equal to 0. This number here will be always equal to 0. So our regression to analyze the standardized coefficients will have only the results of the standardized coefficients for my two independent variables that I have in this example. And where is this standardized beta 1 and standardized beta 2? Right here. So to interpret the result, the effect, the impact of change in age on income controlling for education, we analyze here, right? One additional year of age increases income by $796 on average, controlling for education group. If I move up in my education scale, I increase earnings on average by $16,000, controlling for age. Which one has a stronger effect, age or education? I cannot compare these two guys here because they have different units, right? This one is 1 year of age. This one is education groups. But I can compare these two guys here, right? This is not a minus. I can compare this person here to this other person here, okay? So how do I interpret this? If I increase age by 1 standard deviation, I will increase income by 0.19 standard deviations. What does it mean, standard deviation? It's crazy. It's difficult to understand. When you include dummy variables, it becomes even more complicated to understand. But that's not the point here. The point is that you want to now finally compare the magnitude of these two coefficients. And what does this one say? The increase in 1 standard deviation in the education group increases income by 0.33 standard deviations. So by looking at these two, which this interpretation is difficult to understand practically, but I can say that education has a stronger magnitude on income because it's farther away from 0, right? It's 0.33. And age is 0.19. It's closer to 0. The farther away I'm from 0, the stronger the magnitude, right? So we are talking about the magnitude of the coefficient, and that you do with the standardized beta. And that's the thing, like here Stata calls the standardized coefficient beta, but I have been using the word beta for the coefficient here, for the Greek letter beta, okay? So this one here is beta. Let's continue now to understand the rest of the regression. And this is the same equation that I showed in the previous class to estimate the statistical significance of each one of the coefficients. So I have the coefficient estimated, the beta, that I just had it right here. I estimated it. And now I have to estimate the statistical significance. And to estimate the statistical significance, I will need the standard error of the coefficient. And the standard error of the coefficient, I will estimate it with this formula here. All this formula here. I will get all the values of observed of income for all people in my sample, subtract by the predicted value that I have after the beta is estimated, the coefficient is estimated. I will square them and sum them all. This is the size of my sample size n. And here I will compare, for example, the age of each individual to the mean of age, square, and sum everything. Right? So this, I gave here the example for age, and then afterwards I have to estimate the t-test for education. And then I will do the education of the person here minus the average education for that variable that I'm using. This standard error here will be estimated, and then I divide the coefficient by the standard error, and I have the t-statistic, the t-test. And what we talked in the previous class is that if I have a really large sample size, my n is going to be big here. So this denominator will tend to be small. So my standard error will tend to be small and my t will tend to be big, right? So I will tend to have statistical significance. Having a larger t, I will tend to have more statistical significance for the effect of that independent variable that I'm analyzing on the dependent variable. Another thing that's important for us to talk, which is pretty much the same thing that I said here before. Some people usually mention in their work or in their presentation that they have statistical power. Their regression has statistical power. What does it mean? Statistical power for regression analysis is the probability of finding a significant coefficient, in other words, an estimated beta different than zero, when there is a significant relationship between the independent and the dependent variable in the population, where the beta for the population is different than zero. See that here I have the hat. The hat is the association between my independent and the dependent variable using the sample. Here I don't have the hat, it's in the population. I cannot actually calculate this because I don't have data from the population, the whole census. But let's say that age does have an effect on income for the whole population. My goal is to find that also based on my sample, that coefficient will be different than zero. The statistical power depends on the confidence level, depends on the magnitude of the effect, in other words, the size of the coefficient being estimated, and also the sample size. Because small sample size might not capture enough variation among observations, and then I might not see a significant effect of, for example, age on income. Let's say that just everybody that I interviewed in my sample, my survey, was only people with everybody was 30 years old. So there's not enough variation, so I cannot see if age impacts income or not, because everybody has the same age. On the other hand, if we have large samples, we tend to have statistical significance measured by t, even for coefficients with small magnitude. And that's an important point here. A lot of people say, oh, I got a statistical significance for the association between my independent variable and my dependent variable. What matters for our analysis is not just the statistical significance, it's also the magnitude. Sometimes this number here is going to be really, really small. This number here is going to be really, really small. Okay, it's significant, not necessarily because I have a strong association, but maybe because I just have such a large sample size that it will create statistical significance, although my coefficient is really small in magnitude. So I have to be careful. I have to analyze both. I have to understand the magnitude from here, or ideally from here, and also the statistical significance. What I'm emphasizing here is that large samples can give you large statistical significance even when your coefficient is really weak, okay? So like we same thing as the previous class, a bigger t-test will generate a stronger statistical significance, and the smaller the p-value, smaller the probability of not rejecting the null hypothesis. And that summary table that I used to you in the last class too, here we have the null hypothesis and the alternative hypothesis. The null hypothesis in this case here will be our betas. In that example there, beta 1 equals 0. And here I would say that my beta 1, since I expect people with higher ages to have higher income, I will expect my beta 1 to be above 0, right? And the verb reject, I use it to talk about the null hypothesis, and the verb accept, I talk it to use about the alternative hypothesis. If the probability of not rejecting the null hypothesis is too small in relation to my significance level. I reject the null hypothesis that age does not matter to income, and I accept the alternative hypothesis that age has a positive effect on earnings. And the significance level here is related exactly to my confidence level, to my success rate, right? The one is the complement of the other. And that's what we talked about here before, that the statistical power depends on confidence level, the magnitude, and the sample size. The sample size I talked here, the magnitude here, and the confidence level also affects our test of statistical significance, because we're going to be comparing the P with the alpha. And alpha is exactly the complement of my confidence level. Okay? And if the probability of not rejecting null hypothesis is, sorry, here I said correct, right? The probability of not rejecting null hypothesis is smaller than my significance level. I reject the null hypothesis that age does not impact earnings, and I accept the alternative hypothesis that age has a positive effect on earnings. If the probability of not reject the null hypothesis is actually too big, I do not reject the null hypothesis that age has no effect on earnings. So age, in this case, will have no effect on earnings, right? And I do not accept my alternative hypothesis that age has a positive effect on earnings. In this case, I will not accept, so age does not have that significant effect on earnings. So let's analyze now the statistical significance from the same regression. The same regression used the complex survey design. So this Strata, we have 217 areas there. And here again, we are talking only about Texas. The Strata, as we said, are the PUMAs, the public use microdata areas. The primary sample unit is the household. We have this amount of households and this number of people. If we expand this to the population size, we have 13 million people in Texas with valid information for these variables here. That's why it's below the 28 million or the 30 million. That's the population of Texas, right? This data here is from 2018. This number is smaller than the population in Texas, exactly because not everybody reported having income. People who have zero income or did not report income because they are children, they are not included in this analysis. The coefficients we already calculated before, and now I did not put the comma beta, so the confidence interval was estimated here. The standard error, the robust standard error, was estimated because my complex survey design takes into account the P weight. And I calculated the number here. 11.7 is the standard error for age, and the 179, the standard error for the variable education group. How do I calculate T? T is the coefficient divided by the standard error, right? So 796 divided by 11.73 is 67.89. And then I just go there in the distribution of T using these degrees of freedom. I find there where this 67 is. It's going to be there in this example. And then I go here and I calculate the area under the curve. In this specific example, Stata automatically shows the area of the curve bigger than the positive value of T, but also than the negative value of T. So it also calculates here minus 67 and calculates the p-value. So this area here plus this area here is really, really small. It's smaller than 0.000, okay? The area under this whole curve here is 1 unit. And here, 67 is here, minus 67 is here. So we have the minus here, the plus 67 here. The area under the curve above this, the area under the curve below this is this. So it's really small. Who do I compare the P to? If I have a confidence level of 95%, I will have a alpha equals to 0.05, which is in our table, 95. The alpha is 0.05. Then I compare the P to the alpha. My P0 is smaller than 0.005. So I reject the null hypothesis that there is no association between age and income. And I accept the alternative hypothesis that age has a significant effect on income. When I calculate the area under the two curves here, as it is the standard in Stata, the alternative hypothesis is saying that beta 1 is different than 0. I'm saying that age could have either a positive or a negative effect on age, or on income. And but in this case, we already expected from our knowledge of our population and even the result here that older people will have higher income. So it's positive. When we do a hypothesis test by using the term different, that the independent variable can have either a positive or a negative effect without saying that really clear at the beginning, I'm doing an exploratory analysis. That's because I don't have any idea. But usually we have an idea of how our independent variable is affecting the dependent variable. So we should already say if we expect it to be, the coefficient should be positive or negative. In that case, that's why I mentioned this here. If a statistical software gives only the two-tail p-value, divide it by 2 to obtain the one-tail p-value. Okay, but in this case here, the p-value is so small already that 0 divided by 2 is going to be 0, the same thing. But I might have a small sample that my p could be, for example, 0.07. And in that case, if I did the two-tailed, I would not reject a null hypothesis because it would be 0.07. If I divide it by 2, it would be 0.035. Then it would be smaller than my alpha, right? So if I have a clear hypothesis of including my independent variables in my analysis, it makes more sense to do just one tail analysis of my statistical significance. In this case, I just divided this by 2. If I think that one specific variable has a negative effect, in any case, I just divide it by 2 because I think it would go to this side here. Okay? And how is this confidence interval measured? As we saw in the previous lecture as well. For such a large sample size, the critical value that we use to estimate the confidence interval is going to be similar to the one that we use for normal distribution. For a confidence level of 95%, we're going to have in this case here, t-score, our confidence level, equals to around 1.96, right? So how do I calculate this confidence interval here? I get the t-test. I get the standard error, multiply by this, and subtract 796. So let's just round it up to 2. 11.7 times 2 is 23. 796 minus 23, 773. 2 times 11.7, 23. 23 plus 796, it's around 819. Okay? So that's the how you calculate the confidence interval. When some people in public health, when they report the results from regressions, they usually tend to report the confidence interval. So that depends a lot on the area that you are. And the idea is that if the confidence interval does not contain zero, in this case here, it's always above zero, it means that age has a statistically significant effect on income. Same thing about education. If the confidence interval does not contain zero, it's always above or always below, in this case, always above, education has a statistically significant effect on income, okay? So now we are able to analyze everything. In our field, in sociology and social science in general, we usually report the p-value as an asterisk on the coefficient. If the p-value here is below 0.05, we put 1 asterisk. Below 0.01, 2 asterisks. Below 0.0001, 3 asterisks, okay? But all this part here helps us understand statistical significance. We also report the standard error in between parentheses below the coefficient. So you show the coefficient, the standard error below the coefficient, and the statistical significance as a symbol of stars, depending if P, the size of P, if it's below 0.05, 0.01, or 0.001, okay? The confidence interval, some other people, like I said, in public health, they might do it as well. And then the other part of that regression that we didn't understand, we didn't talk yet, is the multiple correlation, the R-square. The coefficient of multiple determination, the R-square, measures how much of the dependent variable is explained, how much of the variation on the dependent variable is explained by variations of all independent variables combined. R-square is an estimation of the percentage of variation Y that is explained by the independent variables, by all independent variables in the population. The coefficient of multiple determination is an indicator of the strength of the entire regression equation. So we pretty much just estimated by using the coefficient of determination for Y and X1, or the amount of variation in Y explained by X1, and the amount of variation in Y that explained by X2 after it's controlling by X1. I'm just getting this from here. Multiplied by 1 minus the amount of variation in Y that it's explained by X1. And this whole thing here is pretty much the amount of variation remaining in Y after controlling for X1. And again, in this example here, I'm using only 2 independent variables. More independent variables I have, the formula of the R-square will become more complex. And this value here, the amount of variation in Y explained by X2 after XY is controlled, we don't have it yet. How do we estimate it? We estimate it using this formula here. I will go a little faster here, not going into details just because of the time. And overall, the R-square, how do we interpret it? In the partial correlations, if the partial correlations of Y and X2 while controlling for X1 is not equal to 0, the R-square will necessarily increase by adding another independent variable, right? What happens is that since in any real databases, y and any independent variable, they don't have a correlation exactly equals to 0, this number here will never be equal to 0, for example, and this number here will never be equal to 0, exactly 0. The more independent variables we include in my model, the higher will be the R-square. Even independent variables about what's the size of your shoe, what's the size of your shirt, that don't explain anything about, or the color of your shoes, the color of your shirt. That's something that don't explain anything about your income, but if you include those variables that don't matter anything, your R-square will still increase. So the purpose of our regressions should not be to simply increase the size of R-square. We should test hypotheses. We should include the independent variables in our regression according to our theory, according to previous knowledge, according to our hypothesis, right? It's not just including several variables in the regression. The selection of independent variables based on R-square, the size of R-square, might generate unreasonable models. There is nothing in the hypothesis of linear models that require a minimal value of R-square. I usually tell my students, some people use what's called some statistical software stepwise regression. You put a bunch of independent variables and then you let the statistical software choose the variables that have higher statistical significance. Not based on theory or anything, it's pretty much a statistical test. That's really bad. If a student does that for me in a paper for a class or a dissertation, that student will fail, right? Because you have to include variables not based on statistical significance, it's based on theory. If you are doing exploratory analysis, you have to have some idea of why you are including that independent variable, okay? And this is just a transformation of the R-square to get us into the adjusted R-square. When I include a lot of independent variables in my model, my R-square, as I mentioned before, will necessarily increase, will be higher. So say, oh, that's a better model. No, because it doesn't matter if I'm including whatever variable there, my R-square will increase. So this measure of adjusted R-square kind of punishes the R-square if I include independent variables that are here symbolized by K that do not explain much. So K is the number of independent variables in my model. If I increase too much the number of independent variables in my model, and they don't actually have any power and magnitude of effect on my dependent variable, if I increase this too much, my whole denominator will decrease in this formula. So this whole portion here will increase. 1 minus a bigger number will generate a smaller adjusted I-square, okay? So if I include a lot of independent variables, I'm counting here, 1, 2, 3, K is the number of independent variables that I have in the model. If I include too many independent variables that don't have strong effects in terms of magnitude in my dependent variable, then my adjusted I-square can actually decrease even having more independent variables. And I can compare adjusted I-squares for models that have different forms of my independent variables, but my dependent variable it has to be in the same form. In this case here, I'm just using income. I'm not doing log of income or anything else. So that is possible to do. I can, for example, see if a model like this has a better adjustment than this one, it has a better fit than this one here, by comparing the adjusted I-square of the two models. So these portions that I talk now they are shown in the regression in this table here in the top left, and also the R-square is here, the adjusted R-square, and the root of the mean sum of errors. To estimate this table here, if I use the complex survey design, or if I use the p-weight, this table is not calculated. So if I want to see the total sum of squares, the residual sum of squares, and the explained sum of squares, that here is called model sum of squares, I cannot use p-weight or the complex survey design. I have to use the A-weight. Degrees of freedom here is because my model has only 2 variables. The degrees of freedom here is estimated as the sample size minus 1. So these numbers are before here, n minus 1 for the total sum of squares. And the degrees of freedoms for the residual sum of squares is n minus k minus 1. I went fast here, but these are the explanation about each one of them. Explain sum of squares, which instead is called model sum of squares, residual, and total. So n minus 1, this number is here, sample minus 1. And this number here, n minus number of independent variables minus 1, is 127,785 minus 2 variables minus 1 is this number here. This is the total sum of squares divided by the degrees of freedom. We have the mean total sum of squares. This number divided by this is the explained mean of squares. And here we have the residual mean of squares. And this number here, the square root of it, it's this number here. We usually don't interpret much this table here in our regressions, and we don't interpret this one here. But we usually report the R-square, and we can also report the adjusted R-square if we are comparing different models. See that the R-square here is similar. It's the same thing as the adjusted R-square, because the magnitude of the effect of each one of these independent variables is really good. So it was good that I include both of them. If I had included one independent variable that had a small magnitude here, then the adjusted I-square could drop in relation to the R-square. And here I'm pretty much saying that age and education together explain 16.5% of the variation on income. Okay? And I don't interpret the adjusted R-square that way. This is just to compare different models. I compare the R-square as this percentage variation in income that is due to variation in age and education. This is a more technical part. It's pretty much the assumptions that we have in linear regressions. I could have put it at the beginning of the lecture, but I prefer to put it here because I wanted to show the results first. But whenever we are talking about linear regressions, we have to follow some assumptions. The first of them is that we have linear parameters. The regression is linear in the parameters. My X and Y variable, they could not be linear, but the association between them, beta 1, beta 2, beta 3, and so on, they are linear. So the regression model is linear in the coefficients and also in the error term, right? The error term is, it's called the residual, and it can be usually symbolized by this, by the E, epsilon, or the U. It is the unobserved random term. It is the variation in Y that is not explained by X1, X2, X3, and all my other independent variables. When I have a specific values for people that I collect in a survey, for example, let's see this person here has 1 year of education. And let's say that's the income of that person. Let's say just multiply by 1,000. So that person has 1 year of education and makes $5,000. I just say that's it is. These points here are the observed values. Our regression will generate this, this fit here based on all these values that were observed in my sample. This line here is my predicted line of how my income is going to be based on my years of schooling. This example, in this case here, I have income as a function of only education. In this example, I just have one independent variable here in this case, only education. And some of these values that are predicted, is here my y hat, will have values that are higher than actually what I calculated for some people. So if I calculate the residual, which is the observed value minus the predicted value, in this specific case here, for this specific person here, the residual will be negative. That person is actually making less than what is predicted. For this person here, this person is making more than it was predicted. So the observed minus the predicted is positive, right? So the person is making more than it was predicted. Overall, we are going to have positive residuals and negative residuals. And we expect that when we sum all of these residuals, they will tend to be close to zero. That's the overall idea, right? And that's why in that this number here, we would expect it to be closer to zero, right? That's another assumption that we have. Another one is that my independent variables are uncorrelated with the error term. And you can go into more detail on this later. Each one of my error terms are not correlated with the one collected right after it. So for example, if I have a sample that I collected every year or every month, I expect that the answer of that person the next month should not be correlated with the one that they're going to give the next month, right? If I have that, if I put these residuals in the order that they were collected, the order they were observed, and I see a pattern like I have here, then my assumption of uncorrelated observations of the error terms, it's not being followed. Another one, there should be no perfect collinearity between independent variables. In one independent variable should not be exactly the opposite of the other. So there should be no perfect collinearity. And also, there should be no high collinearity between two independent variables. So we should not have the problem of multi-collinearity. If I include two variables that are pretty much measure the same thing, then that will affect the estimation of my coefficients. Maybe my coefficient will still be estimated and the standard error as well. I will see the result, but I will get biased information. Something that I mentioned yesterday. These are the residuals here in this vertical axis. The residuals have a constant variance. You saw in that previous slide that residuals, they can be either positive or negative when we compare the observed and the predicted value. And I expect them to go up and high and low, positive and low negative with the same strength. And we expect this to be for all scale of my predicted dependent variable. If I have, like in this case here, for lower levels of y, I have lower variance of residuals, and then they start to increase, then I have a problem of heteroscedasticity. So I have to do an analysis of residuals to see if my residuals are homoscedastic or not, okay? What's the meaning of linear regression? How do we interpret this analysis? For example, like we were doing so far here, I have a variable, the independent variable age in years of age, or education in groups of education. increase in 1 unit in this variable will cause an increase of beta 1 units in y. If my independent variable is the log of x, the increase of 1% in x increases y by b divided by 100 units. This one here that we use a lot in statistical regression, log of y, for example, log of income. The increase in 1 unit in x will increase y by 100 times beta 1%. This is an approximation. If I want to know exactly the effect of x on y when I have this kind of notation, I take the exponential of beta 1, subtract 1, and multiply by 100. And then when I have log in both cases, it shows the increase in 1% in x increases y by beta 1%. And that's something that we mentioned before. There's some language that varies among sciences. Economists, when they have this kind of effect here, when the dependent variable is the log of the dependent variable but not x, they call the effect, they call beta 1 as the semi-elasticity. When both of them are the log, they call it the elasticity. So elasticity is pretty much how much y changes in percentage terms due to 1% change in x. So it's, beta 1 is just pretty much, the elasticity is pretty much a coefficient from an independent variable that's measured in log terms, and the dependent variable is measured also in log terms. But because both are in log terms, you interpret both sides in percentage terms. This is a table that summarizes that. How you interpret it is the same thing as before. And here we have the example that we had before. The 796 for the coefficient, 16,000 coefficient for age, and 16,000 coefficient for education. The coefficient for age means that when age increases by 1 unit, income increases on average by $796, controlling for education. And that coefficient for education means that when education increases by 1 unit, income increases on average by $16,000, controlling for age. The standardized coefficient is the same one that we estimated before. The 0.19, when age increases by 1 standard deviation, income increases on average by 0.19 standard deviations, controlling for education. The 0.33, when education increases by 1 standard deviation, income increases on average by 0.33 standard deviations, controlling for age. The adjusted R-square is calculated here when we use the A weight. It's not calculated when we use the P weight or the complex survey design, okay? This analysis right now, I used income as a continuous variable as it comes from the American Community Survey. But the problem is that OLS regressions require normal distribution for all my independent variables. And then I can do some analysis of normality to see if a specific variable has a normal distribution or not. And I've really seen a histogram that income is really skewed to the right. It's concentrated on the left, right? A lot of people receiving low income and few people receiving a lot of income. With a histogram, I can see that. With a box plot, I can see that. Most of the people concentrate on the left and few people here outliers. These quantile normal plots, it's pretty much that if my observed values, they touch this line here, they will tend to, that variable will tend to have a normal distribution. I explained that in detail in this slide, and these are examples of distributions that are not normally distributed, right? But this one here has low outliers, but it still has negative skew. And what we want is that this number should be more touching this vertical line. For income, see how skewed it is. Here I have many more people with low earnings than what I should expect. And also up at the end, I have really more people receiving those really high values there than what I would expect. Skewiness. Skewiness is another measure to analyze normality. If it's less than -1 or greater than 1, the variable is highly skewed. Kurtosis, also another variable to analyze if another statistic to analyze if the variable is not normally distributed. If it's above 3, the variable doesn't have a normal distribution. So the skewiness here is above 1, so income is not normally distributed, and kurtosis also above 3. So we can do some transformations. And here, what do we have in our analysis? We want to reduce the concentration in the left, that positive skew. So we have to use transformations in which the Q in these notations here will be less than 1. So it should be one of those. And for income, we usually do the log because it's easier to interpret afterwards, because like we saw in the previous slides, we interpret as a percentage change. So when I estimate the log of income and generate a new variable, it has much more closer to a normal distribution. It's not perfect. The box plot is not perfect, so we have some outliers here. The quantile normal plot is not perfect. Not everybody's like on the diagonal here, but at least they are a little closer to the diagonal line, right? And the skewiness is below -1, but closer to -1. And the kurtosis, it's still above 3, but closer to 3 than it was before it was 27, okay? And how do we interpret it? We're gonna interpret in percentage terms. This is a generic example, and I'm gonna show an interpretation with real data here. So in this case, I have log of income as a function of age and education. So my new dependent variable that I created in my database, it's LN income. I calculated and create a new variable. So now I have this new coefficient for age, the new coefficient for education, and it's usually easier to understand, to analyze the coefficient as the exponential of the coefficient. I can calculate that in a calculator, or in my regression, if I just do here, comma, E form, the exponential of the coefficient is calculated here. This name here, X coef, can be any name. It's just a name that I want to appear here in this column. But this number here, if I take the exponential of this coefficient, equals 1.02. The exponential of 0.33 is 1.40. So how do I interpret it? The coefficient for age that originally was 0.022 is here. And I take the exponential of age, I know that's 1.02. When age increases by 1 unit, income increases on average by 1.02 times controlling by education. And if I want to interpret in percentage terms, I get this exponential here, subtract 1 unit, and multiply by 100. When age increases by 1 unit, income increases on average by 2.28%, controlling for education. If I had just taken this number here and multiplied it by 100, it would have been, when age increases by 1 unit, income increases on average approximately by 2.25%. Usually I tell my students, use either this one or this one, because this is the correct calculation. This one you use more when you're just looking at the data, if you have only this number here. But you don't report this in a paper, okay? You usually, you report in your table, you can report this, you can report this. But you can report this in a table. But when you interpret, you have to interpret this way when you're writing in the paper. And the first time that you make this calculation, just show in between brackets how you calculated it. And then for the other times, you don't have to do it again. Education, the same thing. Exponential of 0.33, when education increases by 1 unit, income increases on average by 1.4. When education increases by 1 unit, income increases by, on average, by 40%. And because this coefficient here is above 0.3, if we just multiply it by 100, see how this 33 is more different than 40? Exactly because my coefficient here has a strong magnitude, it makes these numbers being more different. That's why I should interpret in my text this way or this way. This way here, I can show in the table, okay? I know it's already 2:30, I'm just 2:35. The standardized coefficients for this regression are here, using the log of income, same way that we analyzed before in terms of standard deviation, and adjusted R-square. This is pretty much saying that with the regression, we can predict values for people with specific characteristics. So what's the average earnings predicted for someone who is 45 years old and is in the 4th group of education? If we just apply the beta 0, beta 1, and beta 2, we get that person will make on average $71,000, right? And that's the model using income. And here we have the predicted values of income for people by age. We have this jump in these 5 groups exactly because we have the 5 education groups. And here are the predicted values by education. In this case, we are saying older people make more money. Here we are saying that people with higher education make higher earnings, right? Yeah, so it's less than high school, some college, and grad school. And the log of income, I get the beta 0, the beta 1, beta 2, and I multiply for that same person who is 45 years old and is in the 4th group of education, and we predict that the earnings will be around $44,900. And these are the predicted values of income by age, also increasing by education. And if I just do the exponential of income to have this information here in dollars amount instead of being log amount. So I just see these curves, okay? Increase in age, increase income, increase education, increase income. I can do several analyses with graphs. Whenever I have my variables there, age, education, income. Then I can calculate the y hat, which is my predicted income, and the residual for that regression. In another case, I can use age, education, and log of income as the dependent variable. And then I can calculate the predicted value of log of income from this regression here, and the residual from this regression. Stata automatically calculates that for us, and then we can put this in a graph. And the graph, we usually get the predicted value of y, which is this, by the residual. For that first regression, the predicted value of y, this one, by the residual. It's pretty much a scatter plot. And I want my scatter plot to be as this homogeneous cloud. So my residuals should have homoscedasticity. If they don't have it, they will have heteroscedasticity if there is no homogeneous distribution. For income, as the dependent variable, you see that my residuals are not homogeneous. They don't have a homogeneous cloud here. So I have an issue of heteroscedasticity. This is the y predicted, and this is the residual. For the regression with log of income, I have a little bit more variation, more homogeneous, but it's still not perfect, okay? And here, I'm just not gonna go through everything. We already passed like almost 10 minutes there, but I did the transformation so far of log of y, which was log of income, but I could also include age and age squared, because that would allow us to measure this. An association of age with income that increases until a certain point, but then close to retirement ages, we see a drop. And this is the observed value. This is not regression. That's the observed value of income by age. The observed value of income by age shows me that my regression should include age as age squared. So I can do with the log of income, which is more appropriate, age and age squared. It increases, but after a while starts to decrease, right? And that point where it decreases, if we implement this formula here, we know that's 48, around 48 years of age, when it was positive and then starts to decline. These are the predicted income. The other one that had more variation was the observed. Here's the predicted. And here's in log of income. If I just take the exponential of the predicted, then I have a curve that has both this little curve here going up and then the parabola because of age and age squared. This one here because it was log of income, and this one here because of age and age squared. But still my residuals are not good, even using age and age squared. They still have problems of heteroscedasticity. And this is the showing here log of income and showing here exponential of the log of income. I can also include dummy variables in my models. For example, age is not normally distributed. Instead of including age as single age or age and age squared, I can break age in several subgroups. So I have here, the first subgroup will be people from 16 to 19, and then 2024 until 65 to 92. And based on this variable of age group, I create a series of dummies that will be 1 and 0, 0, 1, 0, depending on my age. And then we can include all of those together in a regression. We usually choose the one, we have to choose one category as the reference that will be kept outside of the regression. Everything else will be compared to that, which in this case would be the group of 25 or 34. Or we could choose the group that has the highest earnings. In this case, the group of, not this one here, this group here, 45 to 54, okay, which is the one with the highest income. Education, the same thing. I have less than high school, some college, and graduate school. I create dummy variables, a set of 5 dummy variables, and then I choose the category here that has the largest sample size. Why I prefer the largest sample size? Because the ones with smaller sample size, if there are specific outliers within that group, it could bias my analysis. So that's why I try to select the group that has the largest sample size, because then everybody tends to have be closer to the mean. There is less effect of outliers within that group. So this is the result of that regression of age group. And this, I'm just indicating Stata that the group from 45 to 54 is the reference. And the second group of education is the reference, which is high school. And here I'm saying that how lower the income is for these age groups compared to the reference category, and how lower or higher the income is for these education groups compared to the reference category. I can also estimate the exponential of the coefficients, and then I interpret. For example, the coefficient for people 16 to 19. People between 16 to 19 years of age have on average earnings 0.10 times the earnings of people between 45 and 54, controlling for the other independent variables. Look that the coefficient is negative, and I'm saying 0.10 times. So that's a little bit misleading. That's the reason that whenever I have these negative effects, I calculate the exponential, but then I transform in percentage terms. So the analysis is easy to understand. People between 16 and 19 years of age have on average earnings 89% lower than earnings of people between 45 and 54, controlling for the other independent variables. Because it's pretty much 0.10, which is the exponential here, or 0.11, minus 1 is minus 0.89 times 100 is minus 89%. So it's easier to interpret in percentage terms because we clearly say lower here instead of these times, which can be misleading. For education, this case you're positive. People with a college degree have on average earnings 1.7 times higher than the earnings of high school graduates, controlling for age. And people with college degree have on average earnings 72% higher than earnings of high school graduates, controlling for the other independent variables. We also have the coefficients. So we usually see here that in this case, specific subgroups have the higher magnitude. As soon as I have college or graduate school, I would tend to have much higher earnings in terms of magnitude. My residuals are a little better, but not perfect, still not homogeneous. And I can estimate even more complex models controlling for a bunch of independent variables: sex, age, education, race, marital status, and migration. I estimated with this model here, with this command, and I have this table for the logarithm of income, and this one showing the exponential. I do not show this table in a paper like this. I organize it. Not all the variables will be able to appear in the same page, so I divide it. Just show sex and age first, and I organize like I told you. I show the coefficient, female, no, I'm showing the coefficient, not the exponential. The coefficient minus 0.43, minus 0.44. It was just a little different because I ran afterwards. The standard error, this number here, comes from here, the 0.007, which is this number here, 0.007. These stars, 3, they are 3 if my p-value is less than 0.01. And for male, it doesn't appear in the regression when I show here, so I add it manually. And the same thing I added for age group, the reference category here, just showing us the reference. I show model, and I ran different models. This model here is controlling for age and sex, and education, all of them. And then the second model control for race, ethnicity, the third as well, and the fourth as well. The third adds marital status, and the fourth adds marital status and migration status. And here I show the standardized coefficients only for the model 4. The way that I show this depends on each project that I have. And you see that I broke it down. And the good thing about Stata is that there is a command, outreg2, that it gets this table this way that appears on your regression, like this, on your screen, and then saves it in a more formatted way to Excel or to Word, a more disorganized way here, with the coefficient, the statistical significance based on the P, and the standard error. All these labels here, I have to add them. I have to put the border on the top, on the left, not have borders on the left, on the right, organize a little bit. But all this work of including these asterisks and the standard deviation in the bottom and the coefficient here, the command outreg2 does it for us. Sometimes I want to show this in a conference. Instead of showing a table so big like that, I can just get the coefficients from my last model, for example, 0.136. For my last model here, it was this one here, age, 0.136, because there I'm showing the exponential, 0.136. It's here in this graph. And I put it for everybody in the reference category. I put it on manually 1. This is an example of a graph that I got the result from Stata, and then I put it in Excel and organized it. So instead of putting one table with all these regression results that people would not be able to read, I can break this regression, this series of graphs that come from the same regression. So age from the one regression, and the other way to show age here, instead of putting the reference category equals to 1, I can put the reference category as this line here, crossing 1. This one is predicted value of income for women, non-Hispanic white, with high school, married, and non-migrants. So that's the predicted value. The higher the age, higher income, and after a specific age, it declines. So I'm doing this using this command in a package that you can install in Stata. And I'm doing this, the predicted values by age. I can do the same thing for men. The same white, high school, married, non-migrants. Same thing. And I can do one that shows both men and women. But in Stata, it's kind of hard to see that well. So I get this result here, and I just organize in Excel. So I put within each age, I put men and women more together. So I can see, okay, both of them increase and then decrease, but men always has higher salaries than women, controlling for all those other variables that we have in the model. So there is a lot of inequality by gender in the labor market. And as age increases, men increase much more. See the gap here. The gap here is much higher than it was here before. So these kind of graphs, they are much more informative to put in a presentation for a conference. You have 10, 15 minutes to present, then showing tables, right? And you can break them down, the same regression, several graphs. Still, with all these variables, sex, age, education, race, ethnicity, marital status, migrant, still issues of heteroscedasticity. And again, these predictive values here for women, it's also controlling for everything: race, education, marital status, migrant. And we can do a table, a graph like this for all different combinations of my independent variables. Can do for African Americans, for Hispanic, for college, can do all variations that I might want. Issues still with heteroscedasticity. The additional materials I said before on Introduction to Social Statistics available in this website. And the specific do file that I ran all the comments that are available, that I use here in this lecture, are in this specific link here. And this link you can also find within this page. Okay. Wow. I went over 30 minutes, 22 minutes. But yeah. I mean, that's just like, it's really hard to condense linear regression one day, but if it was too much material, we have been recording it, and we will post the video on the Sociology YouTube channel. And I will also post the video, as I did already for the previous lecture, in our course website, okay, in the Sociology, the A&M Sociology website, okay? Thank you very much. And I mean, I'm sure you guys have a lot of questions. Feel free to contact me. I don't want to keep you here, and contact Peggy as well. And if you have any problems replicating this analysis by using those do files, just let me know, but it should work, okay? But if anyone has a question now, I can still answer. Okay?
Okay, thank you.
Thank you very much.
Bye.
Thanks.